To implement condition based effectively, modern power plants employ a suite of technologies. Those are vibration analysis. It helps in detecting imbalance, misalignments, bearing wear, or mechanical looseness in rotatory machineries like pumps, turbines, and other motors, providing early warnings before the catastrophic breakdown occurs. And the next one is thermography infrared scanning, which identifies the hotspots in electrical panels, transformers, boilers, or rotating equipment. And it helps in preventing the fire hazards and energy losses as well. And the next one is the lubrications and oil analysis. It examines lubricants for contamination, viscosity, wear particles, providing insights into the health of the gearbox, turbines, and hydraulic systems. And the next one is ultrasonic testing. Capture high frequency sounds which are undetectable by human ear, useful for detecting steam leaks, compressed air leaks, valve issues, or electrical discharges as well. The next one is electrical signature analysis, which helps in monitoring the current and voltage waveforms of the motors and generators to detect the abnormalities in both the electrical supply and mechanical load. And the signal is analyzed in time domain and frequency domain. Any changes in electrical signals indicates the mechanical or electrical issues. And the last one is real-time sensors and IoT platforms. Deploys smart sensors connected through IoT for continuous data streaming, and it provides dashboards accessibility to all management levels, enabling data driven decision making as well. So let's see with the first technique of the vibration first technique, which is vibration analysis, the key method in condition based maintenance for keeping an eye on the mechanical condition of the rotatory reciprocatory machineries in vibration analysis. All rotating equipment generates vibrations as a function of their misimbalance or any misalignment or bearing interaction is caused. If we see carefully observe the graph, the fault bearing exhibits an additional high frequency component around the 40 Hz, which is typical of bearing defects. This shift from baseline vibration indicates mechanical wear, prompting predictive maintenance before the catastrophic failure occurs. So now let's see why these vibration analysis most matter. Because every rotating component vibrates when defects develop, like vibration patterns change often in measurable or any predictable ways. By tracking these changes over the time, vibration analysis helps in detects early degradation and also preventing unplanned outages and improving mean time between failures, reducing all the maintenance cost as well. Some key parameters to be noted or observed are amplitude, which is measured in MMS or RMS. It helps in overall vibration severity, frequency. It identifies source components of the detection of the defects or the fault caused. And the phase angle shows the relative motion between rotating parts, and envelope spectrum reveals the early stage bearing defects, and crest factor statically indicators of impacts or spikes caused. So, and also main types to be noted are types of vibration. These are three vibrations. First one is a free vibration, which occurs when a system oscillates after being disturbed from its equilibrium position. For example, shaft deflection may be caused after the shutdown or regular maintenance is done. And the second one is forced vibration, driven by an external periodic forces. For example, any imbalance or misalignment can be done by the forced vibration. Damped vibration, energy dissipates over time, means due to friction, like bearing damp vibration is an example for the damp vibration. And the main sensors are accelerometer. General purpose vibrating monitoring is done by these sensors, and velocity transducers used for pumps, fans, and turbines. Proximity probe for the shaft vibrations in turbine or any compressor. So let's see the methods of mounting of the sensor. So we have three mounting methods, that is stud mounting, permanent and reliable, used for long term monitoring, and the second one is magnetic based, portable and suitable for a quick service, and the third one is adhesive mounting for the lightweight or temporary applications. So coming to the first one, which is stud mounting, as shown in the figure, a tapped hole is done in the machine or to the welded part. Then the accelerometer is bolted down with with a threaded stud, and it's mainly best for continuous and online monitoring and for the protection systems and also for the detailed diagnostics needed, where we need the detailed diagnostics or monitoring needed, then this method is very apt and suitable. With a high frequency work should be done, and it's also mainly used in turbine generator bearings and boiler fed pumps, critical fans as well, and also in compressor bearings as well. And the second one is the magnetic based, mainly used for portable surveys or semi temporary surveys. In the figure we can see a flat or two pole magnet attaches to a ferrous or a flat surface. The sensor screws onto the magnet, and here it's mainly used when a route based data collection and a troubleshooting needed, or a troubleshooting is done on ferrous housing, and situations where you need speed and repeatability without any drilling of the equipment is needed. So like for example, like if we need any monthly routes for a pump or motor is needed, then we use this method, or for any quick checks after the repair we go for this method, or really comparing to the similar machines we can use this method, magnetic based mounting method. And the third one is adhesive mounting, which is like pads or glue or wax is used for. Here coming to the adhesive mounting, in this figure we can see a small mounting pad is attached to the machine. Then the sensor screws onto the pad. For very light or temporary work it is opted. Here a strong wax may bond between the sensors directly, and it's used for lightweight housing where tapping is risky, and where we have thin machine guards and non-ferrous surface where the magnets won't stick, then we go for this method. And it's also mainly used for temporary or trail tests needed. uh, so now we'll see for next thing, signal processing and analysis. Coming to the signal processing and analysis, the first one we do is the time-based analysis. It analyzes raw vibrational signals over the time, detect transient events like impacts or looseness, and the next one is the frequency domain analysis. It converts vibration data from time domain to the frequency domain using the fast Fourier transform, like where each frequency components corresponds to the mechanical sources like imbalance, misalignment, or any bare wear of the looseness is done. And the third one is envelope analysis. It extracts high frequency signals from a low frequency noise, like it's really helpful for early stage bearing faults. And the fourth one is the order tracking, used for variable speed machines to track vibrations relative to the rotational speed, and ideally for turbines and compressor and fans as well. So now we'll see the what are the common faults and the diagnostics of those faults. The first one is the unbalance. Here, the high vibration at the rotational frequency causes the symptoms are observed, causing the uneven mass distribution around the shaft. So, the solution would be the dynamic balancing. The second one is the misalignment, where it can be identified when the vibration is at high frequencies, which is causing the shaft axis, which shaft axis not angular or parallel of having the parallel offset, and the solution can be done by laser alignment of the coupling. And the third one is the bearing faults, where high frequency vibration in the enveloped spectrum is observed, causing the rolling element fatigue or the lubrication failure. And the solution is for lubricating or replacing the bearings. And the next one is the mechanical looseness, like multiple harmonic broadband spectrum can be observed, causing loose bolts or worn fits or foundation issues. The simple solution is tightening or rerouting the structure. And the final one is the resonance, sudden rise in vibrational amplitude at a specific speed, causing natural frequency coincides with the running frequency. The main remedy or solution would be is modifying the stiffness or damping. So now we'll see the step-by-step process of the vibration analysis in condition-based maintenance. First thing we'll do is the baseline establishment, means creating the reference signature for each machine knowing at the operating conditions like operating speed, operating load, and the ambient conditions. So the next one would be the mounting, where a continuous online monitoring is done, or periodic monitoring is done, means weekly or monthly monitoring is done. Same measuring points, same orientation, same operating conditions, those monitoring is done at the same points. So we should log the router order and use machine tags or QR codes. That's the main good practices for this. And the third one is the trend analysis, where we detect the change before the alarm limits are crossed by using the trend analysis. Plot overall RMS velocity, acceleration, temperature, and selected spectral bands also compared with the time. So then the trend analysis is helpful for the time based. And we need to watch the slow rise in RMS value, and also sudden shift, sudden changes, sudden level shift after repair or startups. Then we need to, the trend analysis shows the with these stable warning and alarm comparisons. The next one is spectrum analysis, means what's causing the vibration. Then here the spectrum analysis will comes into play, converting time signals to the frequency to identify the fault mechanisms. And the next one we is the fault diagnosis, means the confirming the root cause and severity. It helps in vibrational findings, also for the temperational findings, and also for the oil debris by using, and also for ultrasounding and motor current. It checks the mounting, like soft foot or any misalignment is done with the laser alignment, and also considering operational context on the for the load, cavitation, and process changes as well. And the next one is the main thing is done in the last one is the maintenance decision, means what should be done, when it should be done, with what resources, with what process the maintenance should be done. Here all the decisions will be done. It converts all these diagnostics to a preventive work order in the CMMS, with the choosing a corrective action, for a balancing or alignment or bearing change or structural regrouting. So this is the step-by-step procedural for vibration analysis in the condition-based maintenance. For example, if we see take a 500 kilowatt pump with 1500 RPM, the baseline values are it is having 2.3 MMS per second, having RMS value, when no bearing bands are observed. On the week 6, the RMS value is increased to 4.1 MMS per second, and here a misalignment is suspected, and the action it suggested is laser alignment, and also the soft foot is corrected to 0.12 mm. As a uh, as a result, 1.8 millimeters per second RMS value has been corrected, and the bearing temperature is reduced to 8 degrees. So that resulting as no forced outages, and we also have a added alignment check to the preventive maintenance plan. So now we will see the standards and acceptable criteria with respect to the ISO standards, ISO vibration standards, ISO 10816, which is legacy, and also ISO 20816, which is the current standard for setting acceptance for the alarm and trip settings as well. Here we have divided and projected in a way for the table, where we can easily understand for the machine type, which is small, large, and for the turbines or generators, and divided these standards or values in a good, satisfactory, unsatisfactory, unacceptable points, where in the table you can see clearly visualize and segregate the our machine according to the acceptable criteria, according to the ISO vibration standards. And for setting the alarm and trip settings with respect to of these values, this table, for setting the warning, our value should be near or upper to the satisfactory zone value. And for setting the high set points, the entry value should be close to the unsatisfactory zone. Then plan action with the reliability engineering. For setting the trip or interlock, the only for machines where high vibration risk damage, then only we need to set the trip or interlock system valid with the diagnostics as well. For setting for the commissioning or overhaul, the acceptance value should be for the good zone or low zone of the satisfactory at a rated operating point. So by analyzing and segregating our machine with these values, we need to set the alarm and trip settings and applying the standard in practice according to the applicable ISO 20816. First, we need to identify our machine type, then prepare rigid measurement points which by avoiding painted or looseness surface which and document the sensor orientation. After that, measure overall velocity RMS at each bearings, repeat under similar operating conditions and compare to the zone limits of the class, and also start the trend chart. If your values are borderline or jump suddenly, acquire spectra and diagnose the mechanism for any imbalance or misalignments or bearing is done. So with respect to of these values and segregating our system or equipment with the according to the small or large of the machinery, then we need to set the alarms according to the satisfactory, unsatisfactory. For satisfactory should be zone for setting the warnings, unsatisfactory zone which is we need to set for the high set point alarm. Then we need to set the trip or interlock according to the machine or the analysis is done. So in an overall, vibration analysis is both an art and science. With the right sensors, baseline data and analytic techniques, it becomes the most powerful predictive tool in maintenance engineering. Its ability to detect, diagnose and prevent mechanical failures makes it more important in modern CBM programs across all the energy and power sector industries. So this is the main and important technique used in CBM. Now let's